Hi everyone, I'm Emily, and today I'm going to present our work on Piecewise-Smooth surface fitting onto unstructured 3D sketches. This is a collaboration with Rahul Arora, Andreas Berensen, Karen Singh, and Adrien Bousseau. With the increasing availability of consumer VR devices and design-oriented VR apps, we see the emergence of a new possible workflow for designers. Using 6 degrees of freedom controllers, they can sketch and explore ideas for a new design in 3 dimensions. 3D sketches done in VR are beautiful and effectively perceived by viewers. But these sparse collections of disconnected strokes are non-trivial to transform into 3D surface models for further design communication and processing. Our sparse 3D sketches seem at first glance pretty similar to 3D curve networks, which have received a lot of attention in terms of how to surface them. Previous work, such as the work of Zhuang and colleagues, can analyze the topology of the curve network to infer which sets of curves should be lofted into a surface patch. And the work of Pan and colleagues can generate nice interpolating surfaces with curvature that aligns well with designer intent. However, note that these two methods and other methods in this line of work require a curve network as input because they rely strongly on analyzing the network connectivity. But if we take a closer look at our sketches, we will see that it is not trivial to recover clean connectivity information. In our sketches, the strokes do not form a well-connected curve network with precise intersections, and we think that it will be quite challenging to convert them into one. When sketching, artists often don't plan their strokes such that they form a curve network, so there may be small disconnected strokes or disconnected groups of strokes. Oversketching and minor defects in strokes can also make cleanup difficult, akin to the problem of 2D sketch vectorization. So if we lack network topology information, we can still turn to robust unoriented point cloud surfacing methods, such as the recent work of Huang and colleagues, which we will shortname as VIPs in the following talk. This work can find an interpolating or approximating surface to very sparse set of points, such as our sketches, by optimizing a global smoothness energy. Their method can produce a good result for a lot of our sparse 3D sketches. However, the surface is very smooth and lacks characteristic sharp features that are depicted in the sketch. Furthermore, some sketches with prominent sharp features or a very sparse and unequal sampling might be hard to recover faithfully with this method, even in terms of just getting correct shape topology, as you can see here. This is not so surprising, because the problem of recovering surfaces from such sketches is highly ill-posed, as the strokes are a very sparse and somewhat subjective sampling of the surface. This motivated us to design a method that can take additional input from the artists in the form of a low-fidelity surface along with the sketch. This surface that we call a proxy surface serves to disambiguate where the surface lies in the empty space between the strokes. While fully modeling a surface to match the shape of the 3D strokes would be very time-consuming, modeling a low-fidelity proxy surface can be done in matters of minutes with an existing modeling or sculpting software. In cases where VIPs successfully produces a smooth-fitting surface for the sketch, we can also directly use that as a proxy surface. To recap, our goal in this project is the following. Given a 3D sketch and a low-fidelity proxy surface, either created by hand or obtained with VIPs, as is the case here, our goal is to recover a surface that better represents the input sketch. We design our method around key observations about 3D sketches. First, we notice that artists often depict piecewise-smooth surfaces by strategically placing strokes at sharp surface discontinuities, consistent with traditional sketching practices of representing an object through its feature curves. Therefore, we know that strokes not only represent a sampling of the surface, they can also be an indicator of where to place normal discontinuities. Secondly, while the main patches that form the envisioned surface are often delimited by strokes, other strokes lie within individual patches to depict small parts and decorative details. Hence, not all strokes represent a normal discontinuity along the surface. Some strokes lie in the middle of smooth patches of surface, and those can still be helpful in indicating the smooth patch geometry. Finally, 3D sketches can be a bit imprecise, exhibit oversketching or gaps and missing intersections between strokes, as is the case here. So we do not aim for interpolation and instead regularize our fitting to be robust to small-scale geometric imperfection. I will now give a high-level overview of our method, as well as some practical details. In a nutshell, our method seeks which bundles of strokes lie together on a single smooth surface patch and recovers the geometry of each of these patches. This can be formulated as a joint segmentation and fitting problem. I will dive into each of these two aspects before explaining how we solve for them jointly. In the following, you will often see this car sketch with only highlighted parts on half of the sketch. That is because in the case of symmetric sketches, we simply resort to working on half of the sketch and then mirror the result. Let's talk about the segmentation now. By associating the strokes of the proxy surface by a closest point projection, we can formulate our problem of finding how to bundle strokes as a segmentation problem on the domain of the proxy surface. In practice, the proxy surface is discretized as a triangle mesh, and we seek a segmentation of the vertices of this mesh, such as represented here on the right by the rainbow vertex colors. So for each region of the segmentation, we must find a smooth surface patch whose shape closely approximates the strokes. We choose to model smooth surface patches as implicit polynomial surfaces. In other terms, the zero-level set of a low-degree polynomial function defined in R3. We fit surfaces to stroke points by solving for this coefficient vector theta of the polynomial function. Such implicit surfaces offer multiple practical benefits in our context. They have infinite support, allowing the surface regions they capture to grow or shrink arbitrarily as the algorithm progresses, and they are fast to evaluate and fit to stroke points. Therefore, the variables of our problem are of two natures. On one hand, we have discrete variables corresponding to the labeling of every vertex of the proxy mesh. On the other hand, we have continuous parameter vectors corresponding to the coefficients of the implicit polynomial surfaces. The segmentation into regions well approximated by a smooth surface patch and the fitting of each of those surface patches must satisfy the following criteria. The surface patches should run close to the input strokes, both for strokes that depict sharp surface discontinuities and for strokes that depict details within smooth areas. The boundary between neighboring regions should lie along some strokes and not overly cut through strokeless regions. In other terms, the segmentation should be smooth, with boundaries concentrated along some strokes. And the surface should be composed of a small number of surface patches rather than many intricate patches that would overfit to inaccuracy in the input strokes. We formulate these competing requirements as energy terms in an optimization. I will now explain how each term is formulated. So recall first that a given region of the segmentation has a set of stroke points associated to it. To measure how well a surface patch reproduces the geometry of strokes of the corresponding region, we compute square distances between the surface and all stroke points associated to this region. Then we sum the contributions of all surface patches and corresponding regions. About the second objective, we are inspired by classic work on edge-aware image segmentation. And we achieve alignment of boundaries with strokes by encouraging neighboring vertices to share the same label, unless they are separated by a stroke. Concretely, we do that by assigning a weight to each edge of the mesh, using a low weight if the edge is crossed by a projected stroke segment and a high weight otherwise. Smoothness of the segmentation away from strokes can then be measured as a sum of the weight of all mesh edges which lie across a boundary between regions. Finally, we encourage a surface reconstruction to be as simple as possible. We measure the complexity of a given surface patch by its degree, and measure total complexity by summing contributions from all surface patches. This makes a lower degree polynomial less costly than a higher degree polynomial. Also, it encourages using as few surface patches as possible. This optimization problem is non-convex and contains both discrete variables with the segmentation and continuous variables with the parameters of each surface patch. We find a local minimum by adapting the general multimodal fitting algorithm called Pearl by Isaac and Boykov. From a large initial set of surface patches, this algorithm alternates between improving the segmentation by performing multiple graph cuts and refining the surface patches model parameters by surface fitting. It terminates upon reaching a local minimum. In the paper, we also detail a simple strategy to provide some user control over the results of this multimodal fitting optimization. Finally, once we have obtained a set of surface patches, as well as a segmentation of the proxy surface, we obtain the final surface by projecting the proxy surface onto the surface patches. First, we insert edges in the proxy surface mesh along segmentation boundaries, so that the discretization will allow the emergence of sharp feature edges. Then, we project each mesh vertex onto its associated surface patch, while regularizing by encouraging mesh smoothness and boundary polyline smoothness. We tested our method on a wide variety of 3D sketches and curve networks. Sources include sketches done with Gravity Sketch, which is a commercial VR tool, sketches done with 2D interfaces for 3D sketching, and clean curve networks, which were used as examples in other previous curve network surfacing papers. All of these results were obtained fully automatically by using VIPs by Huang and colleagues to generate the proxy surface. Note how our method recovers the sharp edges depicted in the sketch, even from very smooth, approximate proxy surfaces. We compare against curve network surfacing methods represented here by the work of Pan and colleagues, and also against point cloud surfacing methods here with VIPs, the work of Huang and colleagues. Curve network-based methods can recover beautiful surfaces, but only without any degradation, and they cannot easily take into account isolated strokes not explicitly connected to the network, such as those highlighted in red here. Point cloud surfacing methods such as VIPs can only recover smooth surface approximations. In contrast, our method can take into account all strokes and produces a piecewise smooth result similar in quality to the result of Pan and colleagues. By taking a different approach than previous papers focusing on curve network surfacing, our method is designed to be robust to unstructured inputs. We illustrate this by gradually degrading a clean curve network and surfacing it with our method. Artificial degradation, such as oversketching, gaps at intersections, low and high frequency noise, do not affect the result much. However, the robustness of our method to unstructured and noisy inputs comes at the cost of decreased precision in the surfacing. Small-scale details, such as buttons on top of the machine, might be missed, and smooth patches with complex curvature that can be captured by a surface patch model may be ill-reconstructed, as the tubular nozzle here. In contrast, curve network surfacing methods perform interpolation of all the curves, so they are better suited to recover such minute details in cases where the sketch is perfectly clean and structured. Finally, a more fundamental limitation that deserves further investigation lies in questioning our assumptions about how artists depict surfaces with a sparse sketch. Indeed, we focused on the case where the sketch strokes lie on the surface of the object depicted in the sketch. But there are cases where artists employ strokes to signify tubular shapes, such as the feet of this chair. Similarly, a core assumption of our method is that a sharp feature of the surface is represented, at least approximately, by one or multiple strokes. This makes it hard for our method to correctly detect sharp features otherwise, even if other shape cues clearly indicate the presence of a sharp feature, such as a sharp corner on a neighboring stroke, as is the case here on this car headlight. To conclude, we propose a method that can deal with unstructured sparse stroke clouds that designers produce when sketching in VR or with sketch-based modeling systems. Inspired by the unique characteristic of this emerging form of 3D data, we have designed an approach that can produce a piecewise smooth surface aligned with salient strokes. Our surfaces derived from sketches are compatible with all downstream 3D processing and modeling tasks. This opens exciting avenues to integrate 3D sketching with other creation modalities. For example, it would be interesting to imagine workflows where both 3D sketching and 3D sculpting can be used in combination on the same artwork. We think there are many questions to explore in terms of both interaction design and hybrid or linked geometric representations to help artists use a combination of complementary tools in their work. Thank you for your attention. Please feel free to come chat during the Q&A if you have any questions or to write to me.